Okay, so we are on Unit 4, and the topic is virtual memory. The learning outcomes that we're going to cover are as follows. Briefly explain virtual memory. List and explain the hardware and control structures that support virtual memory. Explain the various OS mechanisms that are used to implement a virtual memory. Define paging, and also being able to explain the concept of segmentation. So the last time I saw you, we covered the topic of memory management broadly. And from what we know, virtual memory was a sort of a related topic. Okay. So by now you should have some idea what we mean when we say virtual memory. But they say, according to this slide, that virtual memory is a feature of an operating system that allows a computer to compensate for shortages of physical memory by temporarily transferring pages of data from random access memory to disk. Okay, so your computer is running out of memory. It has to continue functioning. It cannot just crash. Okay, so it needs to make a plan for itself. It needs to make an arrangement. So the concept of virtual memory tends to kick in. And there are different techniques that are used to actually implement virtual memory, and we want to talk about those in this lecture. So how do you support virtual memory? What needs to happen? Okay, in order for you to be able to implement virtual memory, you don't do it, but it's done by the operating system. And it has to, the hardware in the computer must support paging and segmentation. Okay, I think specifically if we're speaking about hardware, we're speaking about the hard drive because that's where this paging and segmentation actually occurs. And operating system must be able to manage the movement of pages and segments between the secondary memory and main memory. So for you to be able to, or for operating system to be able to support virtual memory, it has to, these two things have to be met. The hardware has to support it, and the operating system itself has to be able to implement or make use of that feature or these features. Okay, so some of the key terms that we use in virtual memory. Um, so some of the key terms include, which we already defined what virtual memory is. We said a storage location scheme in which secondary memory can be addressed as though it was part of the main memory. The addresses a program may use to reference memory are distinguished from addresses the memory system uses to identify physical storage sites. Okay, so what is virtual and what is physical? Physical means there is a physical component that you can touch and feel that is present and has memory locations. Virtual is something that's created dynamically. And in the previous lecture, we said virtual memory is actually created by the CPU on the hard drive. So when we refer to as virtual addresses, the address assigned to a location in virtual memory to allow that location to be accessed, though it was part of a main memory. And then we talk about virtual address space. Okay, it's the virtual storage assigned to a process. So the address is sort of a page or a location where a particular process has already been assigned. Okay, and a virtual space is the storage space that it's been assigned to or a particular frame. Okay, then we also have address space and real address. Address space would be a storage location or a frame on the main memory, which then a real address can be assigned to that space. So a virtual address is assigned a virtual address space, and a real address, okay, is assigned to an address space on main memory. Those are the two distinguishing factors about these concepts. So when I throw them around, you don't get confused. So what actually happens when somebody clicks on a program on a computer or a desktop, okay? So a process is initiated. A process is initiated. Operating system brings into main memory a few pieces of a program. So it's not wise for the operating system to bring everything, because not everything may be required now. It may only need to bring certain parts and then request the others on demand, okay? Especially in the instance where there are six main memory frames and there are 6 pages, okay? So if it's just one program being executed, it can take all the pages and place them into the corresponding frames. However, that's in the perfect world. In the real world, users open up a lot of these programs at the same time. So what would happen is that when a user clicks on a program on a desktop, the operating system brings into main memory a few pieces of that program. Then we have the resident set, which is a portion of a process that is in main memory. So once the pieces of this program actually go into main memory, they're then called the resident set, okay, because they're residing now in main memory. An interrupt is generated when an address is needed that is not in main memory. So it triggers what we call a segment or a page fault, because the CPU is now working on this program, it's executing this program from the main memory. Then what happens when it realizes that, look, not all parts of this program are actually in the main memory. So now I have to go fetch the additional missing parts. So we say it triggers an interrupt. Interrupt is a electronic signal sent to the CPU to say, can you attend to me now? And it's not the first time this is coming up, interrupt. We say it's an electronic signal sent to the CPU where a particular device is saying, attend to me now. And interrupts can come from hardware, but also from software faults. So in this particular case, you're executing a program and there's missing bit of it from the main memory. So that triggers the CPU or interrupts the CPU, and it has to attend to this matter urgently, and it has to go make a plan on fetching it somewhere. And we want to talk about this place that it has to go look for these pages later on. Operating system places the process in a blocking state, okay? So the process, we reached a point where we cannot continue because there's something missing. So it's going to put it in a blocking state while it's doing that parallel process of going to fetch the missing pages or segments. Piece of process that contain the logical address is brought into the main memory. So once it finds it, then it brings it into the main memory along with the other initial resident sets. And then obviously, then the program is not, so it was put into a blocking state. So this is a typical flow of what happens behind the scenes whenever you click on a program and it becomes a process. So what are the advantages of having a process? More processes may be maintained in main memory, only load in some of the pieces of each process. With so many processes in main memory, it is very likely a process will be in a ready state at any particular time. A process may be larger than all of main memory. So breaking up your process into segments or into pages is an advantage because the program that you're executing may be bigger than the amount of available space on the main memory. So by breaking it up into smaller pages or into segments, you only send certain pages there and the other ones are requested on demand. So you can see how this paging will work. So we have process A1, process A2, process A3, and process A4. And each one is broken up into pages, equal size pages, okay? So that makes it easier because if we take process 1, it looks like it has 4 pages, and we assign it to a main memory with 8 frames, which means it's going to be taking up half of the frames. Then there's room for process 2 as well. Okay, so we can run 2 processes there. However, the concept of main memory can actually be stretched further, where we can take A1, A2, A3, and A4 instead of taking A1 and taking its first 4 pages and then taking A2 and taking its first 4 pages, which means these 2 processes alone will hog up the number of frames. So what we do, we can just balance out and take a single part of each of these processes just to balance out or the representation within the RAM. It's all about sharing, equals sharing where possible. So paging partition memory into equal fixed size chunks that are relatively small. Process is also divided into small fixed size chunks of the same size. Okay, so in terms of paging principles, the RAM is divided into frames and the processes are divided into pages on the hard drive side. So paging starts at the hard drive side. Demand paging brings a page into memory only when it is needed, okay, which ensures less inputs outputs needed, less memory needed, faster response. Okay, now we have instance where a process, and I already mentioned this, that certain pages are missing, and if the reference of those pages is made, then the CPU will trigger a page fault. But page faults can also come from what we call invalid references. Okay, so you could be making reference to something that's valid, but it's just not in main memory, it's missing, so we get a page fault. But also invalid reference may occur where maybe a page or a request is being made to a read-only, okay, to a read-only page, and a request is being made to that page. So that process will be terminated or aborted because it's an invalid reference. And then segmentation, which serves the same purpose as paging. However, segmentation does not divide a process into fixed size chunks. Instead, it divides a process into what we call variable blocks, which means the pieces, the divisions will be of different sizes. And you can see here that in the main memory, there's the segment that contains the data, the segment that contains the stack, the segment that contains the code. They could be of different sizes. So hence, the main memory will be partitioned dynamically as opposed to fixed partitioning that you get when you are using pages because they're all equal sizes as the frames. Okay, so that's the significant difference between paging and segmentation. Then, of course, we also have demand segmentation, just like how we have demand paging. So we say demand paging is sending only certain parts of the pages to the main memory. Then when you need the rest, you call them via a page fault. Same thing applies with demand segmentation. You send to the main memory the segments that you require now. Then when you need the other ones, you trigger a page fault and you request them. So there is this component of a computer. It's actually a physical chip, and it's called the main memory unit. So hardware device that maps virtual to physical addresses. In the memory management scheme, the value in the relocation register is added to every address generated by a user process at the time it is sent to memory. The user program deals with logical addresses. It never sees the real physical addresses. So we have this component, which is called the memory management unit, and its role is to map virtual addresses to the physical addresses. Okay, because you're starting a process and then only certain parts of your program go into main memory. So there needs to be a device that's keeping track of the missing pieces. Okay, it needs to keep track the resident set along with its missing pieces. It maps that this is still part of the same program, and that's the memory management unit's job. And it does this through what we call a mapping table. And you can see it works hand in hand in this diagram. You can see that it works hand in hand with these components, the memory and the CPU, but it's a separate component by itself. Okay, so we have the CPU with its registers and the ALU and the control unit. Then we have the memory management unit, and it will also need to have some sort of registers inside. Okay, memory data register and memory address register. Remember that our registers are a form of storage, and this memory management unit is storing information about mapping virtual addresses to physical addresses. Okay, so it's going to need the registers in there, and it contains the paging table. It can contain multiple paging tables, and I'll show you how this paging table works in the slides that follow. Okay, so we have this page table which says maintained by operating system for each process. Contains the frame location for each page in the process. Okay, processor must know how to access the page table for the current process used by a processor to produce a physical address. So the processor is the one that when a page fault is triggered, it has to go to the page table to know where the missing frames are actually located on the hard drive. Okay, so again, the mapping table also contains information about where the resident set frames are located in the RAM. So when possible, when the CPU brings into the missing pieces of the project, it assigns them to contiguous frames. Okay, where possible. So it needs to be able to keep track where is the location of those in terms of frames in main memory or the pieces of the program that I've already sent, but at the same time, it needs to keep track of where can I find the missing pieces in the hard drive. So the way that is done is through this page table, and it maps all of these virtual addresses and physical addresses. And then it talks about types of memory, which you spoke about. You said real memory is real, you can feel it, you can touch it, it's physical. Virtual memory is created by the CPU at runtime. And then you also have something called a valid and invalid bit. So how does this fit into the whole concept of virtual memory? Okay, remember the page table that I've just shown you in the previous slide? Well, in terms of binary principles, when a computer sees 1, it says yes. When a computer sees 0, it sees a no. So computers communicate in binary. They understand, that's their language of communication. It's like a switch. And the concept will apply here in the paging table, okay? And assume that this is how a paging table is actually structured. It will contain these pieces of information. And they say during address translation, if valid invalid bit in page table entry is 0, then that's when a page fault is triggered. So assuming that this is an actual page table that is resident within the memory management unit, by looking at it, it has about 1, 2, 3, 4, 5, 6, 7, 8. Let's say 8 pages. Okay. Now, the valid and invalid bit is there to keep track how many parts of this program have already been sent to the main memory. And you can see wherever there is a 1, it means that that page has already been sent. And then there will be also the corresponding frame number to keep track of where or which frame that particular page has been assigned to in the main memory. Obviously, if there is a 0, it means that that particular page has not yet been sent into the main memory, and so you won't find the corresponding frame number. You will just see a 0 in terms of the valid and invalid bit. So how all of this transpires is if there's ever a reference to a page, first reference will trap to OS or create a page fault. The OS looks at another table to decide. Okay, so the OS would look into the mapping in the MMU. Okay, and is it a valid reference? That's the first thing that it's gonna try to establish. If it's an invalid reference, which a reference is made to a page that is protected or a page that is read-only, then it's going to abort that operation altogether. If it is a valid reference, then it's going to continue and establish that, okay, fine, you made a reference to a page that is missing. It's just that this page is not in memory. Okay, so what's going to happen then? It's going to make a plan to go and fetch it from main memory. And now it needs to find an empty frame for that page, for those pages that it needs to bring in. So if we're looking at this example here, let's say we have the first 4 pages that have already been sent. Now it's coming to fetch the 5th one. Okay, so it needs to make as you can see, it needs to make space for the frame number. We need to find this page a frame number. Now, it's very tricky because there may not be an available frame. So then what happens? Then it needs to swap. It needs to decide that, look, certain pages have been there in these frames for so long, they need to go. And it uses different algorithms to do this, to choose which frames to clear. Okay, so swap page into frame and then reset table. Validation bit is set to 1. So we've now fetched the 5th page of this program. And so the valid and invalid bit for this page must now be changed to a 1 because now it exists in a frame in main memory. So that's how this concept of a page table works in keeping track of which pages have been sent to the main memory, which pages are still missing, and where can those pages be found, okay? And that's what we mean but when we say mapping pages or mapping real addresses to virtual addresses. So restart, in terms of page faults, continued, restart instruction, the process now accesses the page as though it had always been in main memory. So now the concept has been achieved. There was a page fault. We went and fetched the missing page. Now we have 5 pages of our program instead of 4 like how we had previously, which means now when the CPU is doing its calculations or executing the program, there will be an additional page there, which means things are going to happen a bit faster. Okay, and now the CPU is gonna have what we call locality of reference, referencing something that's or executing pages that are within the same location. When the 5th page was still in virtual memory, there was no locality of reference. Okay, and again, they're still missing pages, so there's still not much of locality of reference. But when we take a page from its secondary memory location or virtual memory into main memory, it means there's locality. Now the CPU can at least access the first 5 from the local location, which is faster because it creates an interrupt, which means it creates a delay every single time when the CPU has to go and fetch things. It creates a lot of page faults. Okay, we have to always constantly try to reduce the number of page faults. So where possible, we need to increase the locality of reference. Okay, a phenomenon in which a computer program tends to access same set of memory locations for a particular time period, Locality of reference refers to the tendency of the computer program to access instructions whose addresses are near one another. So what happens then when the CPU wants to assign or wants to bring in a new page or the missing pages into main memory, but there isn't any space? And I said that it has to do a replacement algorithm. Okay, this is different to the allocation algorithms that we spoke about. Allocation algorithms can only work if there's free frames available. If there's no free frames available, then a replacement has to be done. And there are a lot of these replacement algorithms. The first one is the optimal policy. Selects for replacement that page for which the time to the next reference is the longest. Impossible to have a perfect knowledge of future events. So this is just assumption based, okay? And the computer will use its own algorithm to decide this, but this is more of a being optimistic, basically. So optimum policy says, let's see which one it won't get used in the near future, and we swap that out, and we bring in this one that we need to swap in. Okay, and they are saying that it's impossible to have a perfect knowledge of future events because the one process that you think won't be accessed in the near future might be the one that the user is going to revert to next. So it's a very risky approach. Then there's also least recently used. Replaces the page that has not been referenced for the longest time. By the principle of locality, this should be the page least likely to be referenced in the near future. Each page could be tagged with the time of last reference. This would require a great deal of overhead. Okay, so every single time we access a particular process, we give it a timestamp, last access. So when we need to swap in and swap out, we look for the one that was not accessed in the near future. Okay, so if we have cache memory, and cache memory can only store 10 processes at a time, we will reach a phase where we need to clean the cache memory because now we've exhausted those 10 frames. So the one that's going to be the oldest there in terms of a timestamp would be the one that got there first, not the 10th one. It's the one that got there first in position number 1. Okay, so least recently used, which one was least recently used in the near future? And then simple as that, the last one is first in, first out. You've been there the longest, you've been in the main memory in this frame the longest. So then when we need to swap, you'll be the first one out, okay? And that's that other algorithm that can be used to replace frames. So the last concept we're going to talk about is the concept of trashing. If a process does not have enough pages, the page fault rate is very high. This leads to low CPU utilization. Operating system thinks that it needs to increase the degree of multi-programming. Another process added to the system, trashing a process is busy swapping pages in and out. Okay, so what is trashing and how does trashing occur? In simple terms, trashing is when a CPU is too busy doing swapping in and swapping out, as opposed to actually executing programs. And as you add more or you open up more programs in the background, you are increasing the degree of multi-programming on the computer, which means also the number of page faults triggered will be very high. Okay, if we go back to this, I just want to go back to this example with the pages so you can see what I mean by trashing. Okay, so let's take an example where it's just process A1 and process A2. And assume that a RAM has probably 8 frames available. So for as long as you're running process 1 and process A1 and process A2, it's fine because process A1 can send 4 of its pages, process A2 can send 4 of its pages, and then we have a total of 8. But now you open up A3, you open up A4 as well. What have you done? You've increased the degree of multi-programming, okay? And what then happens is that now A1 is not going to have 4, it's only going to send 2, okay? A2 is not going to send 4 anymore, it's only going to send 2. A3 is going to send 2, A4 is going to send 2 pages, okay? So it should be making sense now that we say when you increase the degree of multi-programming, you're opening up more programs, you're also increasing the degree of page faults, okay? Because we said a page fault occurs when certain parts of the program are missing in the main memory. So in the perfect example of A1 and A2 alone, there was no problem because there was complete locality of reference. Both of these processes had all of their pages there. Okay, now there's more competition for the limited 8 frames, which means they're going to be shared between these 4 processes, and there's going to be more page faults because look, this one will be missing 2 of its pages, this one will be missing 2 of its pages, this one will be missing 2, and this one will be missing 2. So all the processes would still have 8 pages, 2 pages each outstanding from the main memory. And for that reason, we say that those going to be trashing of the CPU because the CPU will spend more time now going back and forth and fetching the missing pages for all of these programs, as opposed to how it was when there was just only A1 and A2 and all the frames were available locally. Okay, so we say trashing occurs due to the CPU spending too much time doing back and forth between the memory management unit, trying to locate missing pages, updating the paging table, and so forth. Okay, so you're going to see in the curve that we're going to reach a particular phase where the curve starts to slope downwards. Why is that so? So it reaches its peak in terms of trashing and then it starts to slope downwards because by then the virtual memory or the concept of virtual memory will kick in. So the CPU, the more it goes under pressure, the more it goes to borrow more from the secondary memory. So eventually the process of virtualization will kick in and reduce some of this pressure from the CPU, okay? So that is the last concept we want to cover. And so why is virtual memory a desirable thing, okay? Desirable to maintain as many processes in main memory as possible. And it also frees programmers from size restrictions in program development. So programmers don't have to worry a lot about, oh, how much memory is going to be there in the computer when you're running my software, or what other programs are going to be running at the same time as or computing for memory with my program. It doesn't matter because the CPU always has a plan B, okay? It was not going to crash, it's just going to make a plan B. With virtual memory, all address references or logical references that are translated at runtime to real addresses. A process can be broken up into pieces. 2 approaches are paging and segmentation for breaking up this process into pieces. And management scheme requires both hardware and software support. So that's in summary what we covered in this study unit, okay? So I'm just going to stop the recording and provide you with the opportunity to ask questions regarding this study unit, virtual memory.